This lecture is about predicting with trees. The basic idea is that if you have a bunch of variables that you want to use to predict an outcome, you can take each of those variables and use it to split the outcome into different groups. And so as you split the outcomes into different groups, then you can evaluate the homogeneity of the outcome within each group and continue to split again if necessary until you get outcomes that are separated into groups that are homogeneous enough or that they're small enough that you need to stop. The pros of this approach is that it's easy to interpret, and you tend to get better performance in nonlinear settings than you do with the linear regression models we talked about in the previous lectures. The cons are that without pruning or some sort of cross-validation, this can lead to overfitting, and they can be harder to estimate uncertainty than it can be for the linear regression model setting. In general, the results may be variable depending on exact values of the parameters or the variables that you've collected. So here's an example of what a decision tree looks like after it's already been built. So this is a decision tree that appeared in the New York Times during the 2008 elections when Barack Obama was running against Hillary Clinton for the Democratic nomination for president. And they were trying to decide what would be a prediction rule for whether a county would vote for Obama or for Hillary Clinton. And so the way that that happened was that they would build a prediction model that asked questions of each of the different variables that they had in their data set. So the best split happened to be this variable. So if the county was more than 20% African American, then the county was much more likely to vote for Barack Obama. If it was less than 20% African American, then it became more likely that the county would vote for Hillary Clinton. Then within each of these two subgroups, they went and looked for other variables that might split those subgroups out. So on this branch here, the next question was, is the high school graduation rate greater than 78%? If it wasn't, then the county was more likely to vote for Hillary Clinton, and if it was, then it's more likely to vote for Barack Obama. And the algorithm continues in that manner until you've split out into the smallest subgroups that you are willing to consider. And so you see within each of these leaves of the tree, the predictions were quite homogeneous. In other words, Obama wins 383 out of about 450 counties in this case, and Hillary Clinton wins 704 out of about 790 or 800 counties in this case. In other words, these questions split the counties into groups that were homogeneous. Within each leaf, their prediction was likely to come true that that candidate would win the election. So the basic algorithm behind building one of these trees is start with all the variables in one big group, and then you find the first variable that best splits the outcomes into two different homogeneous groups. You then divide the data into two groups, which we call leaves, and the split that you just performed is called a node. Within each split, we then search through all the variables again, including the variable we just split on, and try to find within that group if there's another variable or split that separates the outcome into even more homogeneous groups. You continue until the groups are too small or they're sufficiently pure, in other words, sufficiently homogeneous to stop the algorithm. So there are different measures of impurity, and they're all based on basically this probability that you can estimate. So within a particular group, so in the M leaf, then you have n total objects that you might consider. And you can count the number of times that a particular class appears in that leaf. So this is the number of times that class K appears in leaf M. So that's this probability. So it's p hat for the mth leaf and the kth class. The misclassification error is 1 minus the probability that you're equal to the most common class in that particular leaf. So for example, if it's a leaf where almost all of the counties would vote for Barack Obama, then 1 minus the misclassification error is 1 minus, the misclassification error is 1 minus the probability that you would vote for Barack Obama. So 0 means perfect purity. In other words, there's no misclassification error and all of the counties would go for Barack Obama. 0.5 means no purity because it's not 1 because in any particular leaf, if the counties were overwhelmingly likely to vote for Hillary Clinton, then you would get perfect purity in the other direction. So it's actually when the leaf is perfectly balanced between the two different outcomes, that's when you don't have homogeneity within that particular leaf. Similarly, there's something called the Gini index, which is not to be confused with the Gini coefficient in economics, and it's basically 1 minus the sum of the squared probabilities that you belong to any of the different classes. So again, 0 means perfect purity. In other words, the class has one particular class has probability equal to 1, and all the other classes have probability equal to 0. 0.5 means no purity. In other words, all of the classes are perfectly balanced within each leaf. Deviance and information gain is another measure that can be used, and so it's called deviance if you use log with base e here, and log base 2 is information gain, and it's basically minus the sum of the probability of being assigned to class K in leaf M times the log base 2 or base e of that same probability. Value of 0 means there's perfect purity within the leaf, and a value of 1 means there's no purity. If you go to this link from Wikipedia, you'll have a lot more information about how these measures of impurity are used to separate the values within each leaf. So here's what they look like for a specific example. So suppose we had a variable that was trying to split the dots into the blue and the red dots. If the variable split it in the following way, where 15 of the dots were blue in a particular leaf and only 1 was red, that would be a relatively pure situation. And so misclassification rate would be 1 out of 16, so that's just this one dot here, and so it's relatively low value. The Gini coefficient would also be low because it's 1 minus 1 divided by 16 squared plus 15 divided by 16 squared, which is a relatively small number. And then the information gain is similarly would be, in this case, smaller towards 0 because it's 1 over 16 times log base 2, 1/16, plus 15 divided by 16 times log base 2 of 15 divided by 16. So that's a case where there's a relatively pure outcome in the two groups. We could also look at the case where it's not. So suppose this variable split the outcomes into a leaf where half of the values were blue and half of the values were red. So that wouldn't be a very good split because it's basically a coin flip, whether you're from one class or the other in that leaf. And so the misclassification rate here is 0.5. It's very large. The Gini index is also maximized. It's 0.5. And the information is also large. It's 1. So this would be a split that wouldn't be made because it wouldn't separate the two groups very well on that particular leaf. So I'm just going to show you an example with the iris data. This is a very old data set, but it shows you the idea of how this works. So I'm loading the data with the command data iris, and then I'm loading the ggplot2 library for making plots. So the names of this data set are the different variables that we're going to be using to predict with. Here it's sepal length, sepal width, petal length, and petal width. And what we're trying to predict is the species. So there's 50 of these 3 different species that we're trying to predict with those variables. So again, I always separate the data into the training and the test set. And in this case, I have 45 examples in my training set that I can use to build a prediction model. And the first thing that I do is I'm going to plot the petal width versus the sepal width. So that's petal width on the x-axis and sepal width on the y-axis. And then I'm going to color it by the different species. And you can see there are 3 very distinct clusters here. So it's a relatively easy classification problem. It might be a little bit challenging for a linear model, but not necessarily challenging for this more advanced modeling with the classification trees. So you can fit the model using the train function in caret. So again, I'm training the model. The outcome is species. I'm predicting with all the remaining variables, which is why I have this tilde and then a dot. And I'm telling it the method is rpart, which is R's package for doing regression and classification trees, one of the packages. And I'm telling it to use the training data. If I look at the final model, it tells me what all the nodes are and how they're split, and and what the probability of being in each class is for each split. So here, for example, there's a split that says petal length is less than 2.45. And if that happens, then you, in that case, all of the examples that have petal length less than 2.45 belong to this species Setosa. So you can read those model splits to tell you what the classification tree is doing. You can also make a plot of the classification tree. And so if you just plot the final model that's produced, What it'll do is it'll produce what's called a dendrogram like this. And so it's a little bit hard to read. It's cut off here, but you can see petal length less than 2.45. Then you're assigned to setosa. And so you can follow to the left what happens if the petal length is less than 2.45, and to the right what happens if petal length isn't less than 2.45, and then follow the next split here at this node down to see the total classification for any particular example. A prettier version of that plot can be made with the rattle package. So you use the function fancy rpartplot and you pass it the final model that was fit using caret. And it makes, again, a dendrogram, but now it's a little bit easier to see. So here we see that if the petal length is less than 2.5, we move over here to the left. And if it's greater than 2.5, then we go over here to the right. And then within that split, so once you've already made that decision among those samples, if the petal length is less than 4.8, you go down here to the left, and if the petal length is greater, you go over here to the right. And so this makes it a little bit easier to see what's going on. You can predict new values using the predict function, just like you can with the other linear regression models. Here, the prediction is going to be a particular class label because the classification tree was built to predict a particular class. And so when I pass the new data, testing data, to the model, it'll actually write out the different categories of a species because it's actually predicting the class for each variable. Some notes and further research sources. Classification trees are nonlinear models, so they immediately use interactions between variables. This is important to keep in mind because it's always a model that's built on the relationship between multiple variables. And if you have a large number of classes for a particular variable, for example, that you're predicting with, the models can overfit a little bit. The data transformations may be a little bit less important. If you do any monotone transformation of a continuous variable, in other words, any transformation that doesn't change the order of the values, but maybe makes them bigger or smaller, then you will get the same data splits with the classification and regression trees. This can make the transformations a little bit less important. They can also be used for regression problems. So I showed measures of misclassification impurity. You can also use root mean squared error as a measure of impurity and do a similar classification tree building procedure for building models for regression as well. There are multiple tree building options in R, both in the caret package using the party package, the rpart package, or you can even use this package tree, which doesn't appear in the caret package, but also has a lot of useful functions that can be used when building these models. For more information, you can read in these two books where there's a lot of good information about classification and regression trees, or in this book that's more specifically targeted to this particular prediction algorithm.